Hi, okay, welcome to the continued series on the running microwatt verilator. Except this is not microwatt. This is the Libre-SOC core, but running with the microwatt uh, mini SOC fabric, and that's a big deal. Just saved a huge amount of time. It's only been a day since I did the last video, so um, I just want to go over that. So we've made the key change that I've made to the SOC. I can show if I can grab the file soc.vhdl. A key change is the addition of a new parameter called external core, and that's there. Which, when external core is not defined, then it uses the standard microwatt core.vhdl. But if it is defined as an external core, then it pulls in a component with exactly the same interface as the standard microwatt VHDL core. Then drops an instance of it. Just like now, this is a trick that's done with UART_top for pulling in the open course 1650, 550. And by munging the Libre-SOC test issuer core, I've been able to make it actually do the same thing. Oh, look, there's a fail. That didn't happen with the thing, but at least we're running tests. Test 04 is a fail 3 DIR thing, but it's reporting things. This is absolutely fantastic. I have to have a look and investigate that. So basically, once we've got the ability to have an external core, then I can just pull in a Verilog file, which has exactly the same interface definitions, DMI underscore DRUR, DMI D out, DMI DIN, wishbone instruction in dot DRUR, and blah blah blah, etc. etc. And then literally just do a drop-in placement. Now, what this allows us to do is to not have to mess about creating all of the fabric that's in soc.vhdl. So we can keep all of this the same, use the same UART, the same Zix controller, etc., and all I have to do is to make sure that we'll put in the the external IRQ is pulled at the same time. And because we've been keeping very reasonably close compatibility with microwatt, it's actually all fine. So the only thing is you can see it's horribly slow. It's 2, 3, 4, 9, dum, 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 dum. Yeah, it's 2 characters a second. And just, come on, you can do it. Now the reason for that is because we're still running this I'm still running this test with the finite state machine based version of test issue, which we threw together very, very quickly to get a test ASIC up and running. And it's equivalent to the equivalent thing to technique to Pico RV32, where you just do clock 1, fetch an instruction, wait until that's done, clock approximately 3, pass it to the decoder, wait until that's done, clock 4, pass that to the core, clock 5, get it decoded, see what registers are needed. Clock 6, fetch register A. Clock 7, fetch register B. Clock 8, fetch register C. You get the general idea, and it meant that we don't have to mess about on a very short timescale with things like pipelines or overlaps or um, hazards or any of that stuff. We completely cut it out. Thing, and we'll be doing that, sorting that out for next year. We're currently developing an in-order core, but here's the thing: whilst doing that in-order core, I can still, in parallel with Cesar developing it, I can still run these MMU tests here and all of these things because it's just executing. It doesn't care how fast the instructions are actually executing. So yeah, it's up to test 12. This has been 11 pass, 12 pass. I had that working last week, number 4, test 04. So I'll have to have a look and investigate that and find out what's going on. But that is a data test. It's now, I think tests 1 to 11 are data and 12 onwards are instructions, if I remember correctly from looking at the code. So that's a good sign that test 12 is 13. Look at that actually. Let's have a look. VI tests MMU MMU.bin. Whoops, MMU.c, not binary. Find test. Which one was it? Test. MMU test 13. Create a page table entry. Oh, yes, it is. It's test. It's execution. Yeah. So from 11 onwards, it starts to do execution side, which is the instruction fetch. And oh look, you can see here this one, test 12 is setting instruction relocation, which is virtual memory for the iCache. But despite the fact that it's horribly slow here, we are actually running with the MMU and with the iCache and the dcache. I'm going to have to spend tomorrow investigating that that data file, MMU test 4, and then it'd be worthwhile trying out the to run Linux, to actually boot Linux with Libre-SOC core. I mean, it's going to be unbelievably slow, but we will have, and you can see this, I was looking at this earlier, we have the GTK wave traces, and here you can see I can drill down, and that's the decoder, that's the Libre-SOC core decoder, the power instruction set to decoder. You can see, cache RAM. That's for the instruction cache. Instruction cache or data cache, etc., etc. And you can into the function units. There's about 10 pipelines here. We just had to do separate pipelines. So there's trap, SPR, shift rotate, mul, MMU, logical, load store, divide, condition registers, branch, and ALU. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 separate pipelines because we're going for a superscalar design. And that will allow us to do overlaps. So it's all there. Absolutely brilliant. Anyway, thank you very much.